computer science department at the University of Hawaii, Manoa. And I believe it's going to be talking about using global circulation models and deep learning to predict sea surface temperature. Thanks, Anton. Take it away.
Thank you for introduction. Can you hear me well?
Yes.
Okay. I'm a master's student at University of Hawaii, working mainly with Peter Sadowski, doing different deep learning projects, and today I'm going to be presenting one of them. As an introduction, I'll tell you a little story. Me and my partner a year ago went to New Zealand, and we went to a Mount Cook National Park, and we went right here because we wanted to see the glaciers. And here's the picture from that spot. And you might be asking two questions. Why do I look so upset? And where's the glacier? The answer is the glacier is gone. It is, that's another example why climate forecasting is important. But next question is, why is sea surface temperature relative to climate? And there are a couple of reasons, and also there's more reasons why it is important. One reason why it is important for climate, because it affects global weather patterns such as El Niños and other ones that are appearing in the Atlantic Ocean. Another thing is that it's quite complicated question how to measure the temperature of a planet. Good thing is the water is about 70% of the surface. And if we want to measure the surface and we just measure the sea surface temperature, we're 70% done with measuring the temperature of the surface of the planet. And also ocean affects the Arctic and Antarctic ice sheets that are basically working as a cooling system. Another important reason to be able to analyze the sea surface temperature is because it affects marine life, because in cold water, phytoplankton is able to reproduce, and it is one of the sources of nutrients for other marine life. So what has been done before to answer, another notice, so the first area, the biggest one, is one where El Niños arise, and this is one of the areas of interest for climatologists, but our model mainly was aimed to predict sea surface temperature into those two areas, northern tropical Atlantic and the eastern equatorial Atlantic. Why? Because it affects the global weather patterns that affect the east coast of the US, among others. And now let's get to the classical approach. Classical approach is two relatively simple models that we're comparing to. And so F prime is the sea surface temperature anomaly at time step t. And it's basically how different our current observation at the time t, how different it is from the climate at time t, which is the normal temperature at that time. Specifically for our experiments, it's the month. What is the average January temperature in this particular area? And first simplest model is just to predict it as persistence model. So basically predict that next time step is anomaly is going to be staying the same as at this time step. And more advanced model that is better performing and considered kind of industry standard is damped anomaly. And it is basically autoregressive model where we train the parameter A to be matching our data, and A is basically reducing the amplitude of this anomaly. And great thing about these models is that they work well with the few data points, because we have good observations of the climate data that is on the fine grid since I think 60s or late 50s. So it's about 60 years. And 60 multiplied by 12, 720 data points. Not that much space for big neural networks to train big model and get fancy. So this models work well. But what we are doing is we're using a Canadian ESM2 model, and it consists of atmosphere ocean model and then 2 carbon models, and they all coupled to basically generate a simulation that will give us 800 years of data. Compared to 60 years of real data, it's great, and it enables us to train pretty big neural network with convolutions. And now let's look at what we do with this data. We use first 600 years or 7,200 time steps as a training data every time for every single network. And then we use next 100 years as a validation set to train the hyperparameters and to use it for early stopping. And then we looked at the different hyperparameter settings and estimated their performance on the test set. After that, we retrain the best model that performed the best on the test set on the 700 years and used last 100 years for early stopping, and then compared it to damped persistence to the second model here on the real world data. And as you can see, we do not use any real world data to train our model. We only use it for prediction, which is, I think, a very exciting part. So this is how the data input for one single time step looks like. And you can see the continents here. It is 120, I think 128 by 22 grid. And in each grid, we have a recording of sea surface temperature or sea surface temperature anomaly. And what we are going to be inputting in the neural network is a certain number of steps of previous climate states. And we're trying to predict half a year of the development of the climate and then estimate how well it does.
Sorry, real quick, Anton. What's the MSE there again? I'm sorry, I missed that.
So MSE here is mean squared error if we use that input in the persistence model. So if we just left it as anomaly persistence, that's what the MSE would be for the next step, into predicting the next step.
Thanks.
Yeah. So our neural network is accepting the tensor that has first two things. It's the maps like this. Then there are channels that represent certain amount of time steps, and number of time steps was a hyperparameter. And at each time step, there's 4 observations. There's sea surface temperature anomaly, there are wind anomalies, main components anomalies, and there's Z20, which is basically how deep do we need to go in the water to reach certain temperature. And this last 2 parts are packed into what is considered color channels in the image processing neural networks. So at each location, there's 8 observations. And we came up with this architecture that has a bunch of convolutional layers, and then it does a trick similar to a UNet when it concatenates the input again as another layer and passes it to the next network that is shallow compared to the first one. And then another trick we're using is we're adding the input again to the output of this convolutional network, kind of trying to imitate the persistence. And then as the output, we're basically getting the same map that generated the generated predictions. And here are the hyperparameters that we went over, number of inputs, time steps. And the interesting thing is that it almost doesn't use a lot of time steps, so it's almost working as damp persistence in the sense that it disregards most of the historical information. And then we used Sherpa library to use by Bayesian optimization to train. There were some hundreds of neural networks, I think 400 neural networks. We used by Bayesian optimization to find the network that is going to be performing the best on the still on the simulation data. And as a result, for the regions of interest, we perform our model performs significantly better than the persistence model, than the simplest model, and this is averaging over 6 months. So it is doing better both on the climate model data and on historical data. But when we compare it to the damp persistence in those 2 graphs, we can see that in one of the regions, it still does better on every single month, and in one, it does basically as well. That is pretty exciting result because we didn't use any of historic data to train the model, and basically you almost can say that it is a result of a certain thought experiment, except for obviously the models that we were using were created based on certain observations, and they were calibrated based on the existing climate. So that is the information that is, even though it's not used implicitly, it is used explicitly. Anton,
why don't you explain those plots a little more?
Yeah, so it's basically the accuracy in root mean squared error over, so our prediction and input month was February. That means we also included the January, and we are looking at how well we can predict, how well we are predicting next 6 months. And it is pretty reasonable that it is decaying because it's harder to see further in the future. And a root mean squared error also is representing that. But basically what we can see, the biggest difference is in those in northern tropical Atlantic. It gives us around 0.4, 0.3, 0.4 of root mean squared error. So basically we're mistaking, but our mistake is less than half a Celsius, which is less than 1 Fahrenheit.
So this seems like there's performance is a little different. I mean, the NTA results are better than the ATL3. I mean, they're both good, but is there any, do you have any feel for the dynamics, or is there a reason physically why that there might be different performance?
So
the ATL3 region is particularly interesting to people because it's where hurricanes start that end up hitting the East Coast. And so there's a lot of interest in predicting what's going to happen in the ATL3 region in order to do hurricane forecasting. So the original goal of this project was to see if we could do better prediction of ATL3 in order to do that forecasting. And this is kind of a negative result in that, you know, we trained this big fancy model and we weren't able to do better than the simpler damp persistence model in that region. But in the North Tropical Atlantic, which is an easier region, we are able to do better than the simpler model.
So the dynamics are more complicated in the ATL3 region. Is that, or was the persistence model you used, did you calibrate that yourself, or is that something that's kind of established that maybe was fit for that region better or something?
It was established. It's not. It's fit for every single point on observations, but it's fit on a very small amount of data. And one of the, like, I can only speculate why it does better on the NTA compared to ATO3, but one of the versions is because of the this is mainly surrounded. NTA is mainly surrounded by the ocean, and ATO3 has way more continent around it. But that it is a speculation.
Thanks.
So we also have tried many different things. Like we tried to input locally connected layers here, and it didn't do better. The hope was that these layers will be able to catch the local differences between the geographic locations. So basically the one what I was talking about just a minute ago. And another thing we tried is using the landmass mask as an input and including the month information into the input. And this did not produce a result any better. Also, Z20, we were told that it is not very accurately recorded, and it produces a lot of noise. But our models with Z20 was performing better than the one without. So that was our experience. So as a conclusion, I want to say that the most interesting thing in my personal opinion is that we can train the model using the simulation data. But again, it's not just a result of thought experiment, because we understand that the simulation simulation was created based on the real world data, but it is basically some sort of bootstrapping that we can do in order to increase the amount of data if we need to, if we want to train a bigger model. And in the simple region, we got the on the NTA, we got the forecast that outperforms the damp persistence, in ATO3. It just did as well, even though it is a more complicated model. And thank you very much for your attention. Now I'm happy to take the questions.
Yeah, thanks a lot, Anton. That was really good. Are there questions from the audience?
I have a quick question.
Yeah.
About the plots that you showed on the accuracy and the RMSE.
Yeah.
Are those computed with respect to the output of the climate model or with the historical data?
With the historical data.
Okay, and so it might be a stupid question, but why is it that the RMSE plots, they are like reducing with respect to future predictions? Like if you go from February to July, the RMSE is somehow getting better?
It's actually a good question, and the answer is because there's less variance in certain months, and some months are way harder to predict, and that's exactly what we see here.
I see. Thank you.
Yeah.
So a quick question about your network. Did you have to do a lot of work to come up with the architecture you used? I mean, was that something you spent a lot of time on, or were the results pretty robust to the architecture?
Architecture, the results were varying a lot based on all the sets of hyperparameters. Also, the part that is not included in this table, but it's in the failed approaches, that all those steps were including different architecture adjustments, and basically the architecture optimization with respect, hyperparameter optimization with respect to architecture was like taking me the most amount of time, I'd say. And it is still, it's always hard to tell when you're done with the architecture search, because there's so many options that you can try. And for example, here I would assume that maybe we weren't done with the architecture search on the number of convolutional layers, because it hit the bound, which is usually not a great signal. But the memory representations of all these maps were basically taking a lot of GPU space, and when there's basically a technical reason why this is the bounding number of convolution layers. But answering your question, yeah, a lot of time was spent. It was Peter's idea to do the concatenation, and basically to do tricks similar to UNet, and the one I think similar to AlexNet, I might be wrong, to add the persistence here and imitate the persistence here, and to do the concatenation layer.
Could you explain more about the Sherpa here? Or it's like, Bayesian optimization. So is it some kind of accessible tool for any kind of problem, or is it more like specific approach for your problem?
It is actually pretty universal. So basically, whatever hyperparameter search you can do in a for loop, iterating over different number of convolution layers, or trying different kernel shapes, or trying different activation functions, basically any hyperparameter. And even by the end of the experiments, I managed to encode the different architecture choices into as hyperparameters and different types of input. And basically it takes all this giant hypercube of in hyperparameter space, and that's the Bayesian optimization on that. And the great part about Sherpa is that it supports out of the box cluster parallel. We're using Slurm as a scheduler, and it is integrated to work with it automatically. So we basically we're able to schedule a bunch of, there was a manager that was scheduling a bunch of jobs that were running different models in parallel. And basically you can speed up the experiments pretty fast.
So you're saying that it can apply to PyTorch or TensorFlow and other.
Yeah. So basically, it is you just have to create a small wrapper for your code when you encode all this hyperparameters as Sherpa variables, and then run the Sherpa master node that is going to be assigning the experiments to different parts of the cluster. And basically, if you pass it as an integer, or if you pass it as a float, if you pass it as a categorical variable or a string in Python, you can, let's say you pass it to PyTorch model, or you pass it to the TensorFlow model, you can use Sherpa to do that. You can probably, actually, no, I'm not sure about if you can run it with Joule. So basically, you just, instead of putting all these hyperparameters in the for loops, or just trying them manually, you create a little dictionary that has the ranges of hyperparameters, and then the main Sherpa algorithm that is, I was using Bayesian optimization, but it also supports the grid search, local, I think local grid search, random search, and population-based training. There's no particular reason why I chose Bayesian optimization, but it supports all these different optimization algorithms, and works pretty great.
Okay, thank you.
Okay, thanks. So I guess unless there's any really pressing question, we'll go ahead and start transitioning over to let Amin get set up.